Second question for day 12. We're still talking about springs, but we're now talking about spring energy and spring potential energy specifically. Good news is this guy is short enough, just like the last one, that the two fit on the same page of my notes. So let's go ahead and get started on it. For this question, I have a pinball machine, and I've got a spring with my pinball on it. And that spring is going to shoot the pinball up a ramp into my pinball game. And what I want to know is when I release that spring, what is my velocity when I get to the top of my ramp? So I want it to go a total distance of 1 meter. And along for that distance, it is happening along a slope that has a 6-degree angle to it. I am given the mass of a pinball of 0.08. That makes a whole lot more sense. 0.08 kilograms. And what else am I giving? Oh, I'm given that the coefficient, my spring coefficient for my spring is 120 newtons per meter it's pulled back. And there it goes. I needed the distance it's been pulled back. So this spring would like to be, if there was no pulling back on it, it wants to be a total distance of 4 centimeters longer. Okay. So the reason we can't just use our sum of forces equal to ma here is because my force from my spring is going to change as it extends. So if we had calculus, we could look at that because we have a varying force as it moves. We don't have calculus in this class, so we cannot approach it that way. However, we can approach it using what we know from our energy equations. So what we can do is we can say that our overall energy, we now have an extra piece added to it. So our potential energy, which is our gravitational potential energy at 1, plus our kinetic energy at 1, plus our potential energy of our spring at 1. So this is our new piece, plus our work going into the system, work done on the system is going to be equal to our potential energy gravitational at 2, plus my kinetic energy. Doing my best here. The screen is not actually horizontal, so if I go off the board, I apologize. Plus my potential energy of my spring times 2. Ugh, that's a mess. Well, what can I get rid of? Work. Friction or outside items acting on this. The spring is acting on it. We are considering the spring as an energy there. A lot of work could be broken into different pieces. When we're talking about our frictional work, it's normally going to become heat. But work is going to go away. That was an easy one. Well, let's say that our pinball at the start is at a height of 0. That lets us get rid of our gravitational piece right off the bat. Well, right at the beginning, we're not moving. Our ball is just sitting there. We're about to release it. We have a kinetic energy at the top. We have a potential energy because we've moved up. But we don't have any energy stored by the spring because the spring is already sprung. So that's taken care of. So this terrible equation that is super long each time we write it out, we're normally only working with a handful of pieces from it. So potential energy of the spring initial becomes potential energy of gravity and the kinetic energy. And we know we're after, well, I haven't written what to find anywhere on the board. We have our what to find. We have our velocity at state 2. So this guy is this pinball is state 1, this pinball is at state 2. Okay, so, and the kinetic energy has the velocity in it. So we're solving for this. Let's start with the new one, potential energy of the spring. And I'm just going to solve for each of these, and then I'll write it back into the equation. So I will say that my potential energy of the spring, which is my new equation, potential energy of a spring, and we're specifically talking about a spring at 1, is 1/2 our spring constant times our delta x squared. Delta x being how far we have stretched or compressed our string. So in this case, we've got 1/2 times our k, which is 120 newtons per meter, times our delta x, which is 4 centimeters. We're going to have that in meters, 0.04 meters squared. Okay, with that, that is going to give me a spring potential energy of 0.096 joules. So that's the amount of energy that I have stored up in this spring that I'm going to use to push the ball. Okay, so that's that one. If we want KE, we also need potential energy of gravity at 2. This one, I normally am just going to write PE, and on the spring, I'll have the S. For this day, I will write the G, but I don't want you guys to get confused. So I've got mass times gravity times my height at 2. My height at 2 is not 1 meter. I am going to need to get an actual vertical height because gravity does not care that I have moved in this direction. Gravity only cares about if I've moved up and down. So this value, this is my height. And looking at this triangle, I know this is 1 meter, and this guy is across from it. So across is going to be a sine function. So height is going to be my total length, my 1 meter, times the sine of my 6 degrees. This guy comes out to be equal to approximately 0.105 meters. So it's 1/10 of the meter, so 1/10 of the potential energy if we did it the other way. Good thing we didn't miss that. My mass is 0.08 kilograms. The gravitational constant is 9.81 meters per second squared. And my height is 0.105 meters. That should all multiply together to give me a total change in my potential energy. Well, my potential energy 2, it is change in potential energy because the first one was 0, of 0.082 joules. Okay, I've got this guy, so this guy is taken care of, this guy is taken care of. I want this, but that is enough to say that my kinetic energy at time 2 is going to be equal to my potential energy of my spring at 1 minus my potential energy of my gravity at 2. Some of my spring energy has gone into gravity. The rest has gone into how fast I'm going. Again, this is keep in mind this is only working since this is a frictionless surface. Otherwise, we would have a work done by friction there. This guy is 0.096 joules minus 0.082 joules gives me a kinetic energy of 0.014 joules. And then we've already practiced turning kinetic energy into velocity. Kinetic energy 2 is equal to 1/2 mass times velocity squared. I want to solve for velocity, so my velocity is going to be equal to the square root of 2 times 0.014 joules, that's my KE2, divided by my, and the half became the 2, divided by my mass, and my mass is somewhere on this board, 0.08 kilograms. And I get a value of 0.59 meters per second. And that was my what to find. I'm all set there. Okay. One little piece to keep in mind here. We are not rolling. This ball is now just moving like a hockey puck. In this piece, assuming there's no friction. We will potentially come back to a problem like this a little bit later in the class where we add rolling, and that will actually change this equation slightly. But for now, this is all you really need to know. This is what I'm talking about there is a exam 3 topic. But yeah, hopefully that was helpful. Take care.